Today I'm going to talk to you all about the geometry of the complex number arithmetic. So we now know a couple of forms for complex arithmetic. We have the coordinate form, the rectangular form, sometimes called as the binomial form. In the previous chapter we talked about polar coordinates. Well, if you simply insert cosine theta and I sine of theta, then we call that the polar form. And then we also have what's called as the exponential form. For complex addition, we already know what that looks like in rectangular form. It's simply multiplying the real and complex components. So let's look and see what that looks like geometrically. In this example, suppose we want to add z1 and z2. Here I've already figured out what those look like algebraically. Now let's see what the geometric interpretation. First, I've graphed the vector z1, again coming from the ordinate, going to the value 3, 3 in the complex plane. And then I've graphed z2, which is 2, 2 in the complex plane. Now what I've done over here is actually make copies of z1 and z2. They simply are color-coded. And what I'm going to do is create this parallelogram here. Now, what you'll see is that z1 plus z2 actually ends up being the diagonal of the parallelogram created by the two vectors z1 and z2. And the subtraction, z1 minus z2, simply ends up being the other diagonal. Now, you may say, well, I can see how that z1 plus z2 is simply 1, 2, 3, 4, 5 over and 1 up, but how does z1 minus z2 actually look like 1 plus 5i? Well, again, a vector only has two things, direction and length, so we can move it anywhere. Here is z1 minus z2, and if I move it to the origin, you can see that that is going to be equivalent to over 1 and up, 1, 2, 3, 4, 5. So that is indeed 1 plus 5i. Now, back to what we talked about a little bit in the previous chapter, and that was the concept of distance. The distance between two complex numbers z1 and z2 is given by the modulus of z1 minus z2. Now remember that the modulus of z is given by the equation x squared plus y squared, where x represents the real part of the complex number and y represents the imaginary part of the complex number. In two dimensions, we know that the absolute value of x minus a, so here we're switching to x and a being a real number, you should know, of course, that that represents the distance between any two real numbers, x and a. We're ultimately going to want to talk about what the idea of the distance between two complex numbers are. So we'll go first talk about real numbers. Here again we're talking about real numbers. So what does the absolute value of x minus a equals b mean, where x, a, and of course b would be real numbers? Well, what that yields is all points x with the distance b from a. So that's of course what we mean by the absolute value of x minus a, b, and b. Here's a small example. If we're looking at the absolute value of x minus 3 equals 2, what we're actually looking for are all the values x whose distance are 2 units away from 3. And of course the solutions to that will be 5 and 1. Now let's go back to complex. If this is what we have for real numbers, then what would it mean for complex numbers? Remember, real numbers are just graphed on the number line, but complex numbers, of course, are graphed in the complex plane. So what does the absolute value of z minus z naught equals r if we're talking about complex numbers z and z naught and r being a real number? Well, similar to what it means for real numbers, it'll give us all the complex numbers z whose distance from z naught is r. Let's look at an example to clarify that situation. Given the equation of a circle K, centered at 1 plus 2i with radius 5, how can we actually represent that? Well, again, when we're talking about circles, we're looking for all points z whose distance away from 1 plus 2i equals 5. So here's a way for us to represent that equation. Now, what if we want to identify a point on K? K being the circle, of course. Well, then we will be trying to find points x plus iy that satisfy this equation here. Again, we're talking about for complex numbers, thus we're in the two-dimensional plane, and circles make sense. Well, we can simplify that to here, and remember the formula for the modulus of a complex number is given by the square root of the real part squared plus the imaginary part squared. Doing this, we see that a sample solution is 4, 6. Again, this is a point on the circle, so there are an infinite number of points. You could choose several. I just chose 4, 6. As long as it satisfies this equation, it will be a point on the circle. Lastly, the question is to find an equation in rectangular coordinates for this circle. Well, you should recall that the equation of a circle centered at PQ with radius r is given by x minus p squared plus y minus q squared equals r squared. So in our case, from part A, we know that the radius is 5. That's the distance away from the center. And from part A, we know that the center was 1 plus 2i, which of course we can represent as 1, 2. Hence, the equation of this circle is given by the formula here. Next, let's talk about another theorem that we have for real numbers that translates very nicely into complex numbers, and that's the triangle inequality. We know that for any points A, B, and C that form a triangle, the distance from A to C is always less than or equal to the distance from A to B plus the distance from B to C. In fact, we also know that the only time we get equality for this equation is when A, B, and C lie on the same line. This property or theorem translates very nicely when we talk about complex number plane, and it comes, quite frankly, because of the geometrical representation we have for complex numbers. So here we go. For all complex numbers z1 and z2, the modulus of z1 plus z2, remember that's the purple one here, is always less than or equal to the distance from z1, the length of z1, plus the length of z2. In this case, we have that as the red one. Makes sense. Here's your triangle. It follows directly from the property for real numbers. Earlier in the previous chapter, I talked about multiplication of complex numbers in binomial form using rectangular coordinates. And we had this formula right here. That form is very complex. But one of the reasons we love polar coordinates is because of what multiplication and division look like. If z1 is r1 comma theta 1 and z2 is r2 comma theta 2, then to multiply these two complex numbers, we simply multiply the modulus and then add the angles. For division, we simply divide the r1 over r2 and subtract the angle. These formulas are derived from the binomial formula on page 57 of your textbook. You should look at it. Quite beautiful. Here's a quick example with a geometrical representation as well. Here we have z1 equaling 2 comma pi over 4. Here we have z2 in polar form. Of course, in polar coordinates, this should be a 3 as well right here. This is simply 3 comma 3 pi over 4. So z1 times z2 is 6 pi, and 6 comma pi, and z1 over z2 is 3 halves comma negative pi over 2. So in orange I have z1. In green I have z2. What happens when you multiply them is they simply add these two angles together. So the angle from the real axis to z1, that angle is pi over 4, and then the angle from the real axis all the way to z2, that angle is 3 pi over 4. And so if you add those two together, you'll get pi. And then it's just multiplying the actual length, or the distance from the origin. And then in red, you'll see the actual quotient of z1 and z2. Well, if you had to look at powers in rectangular form, it would be an absolute mess. But similar to how nicely multiplication and division transfer from looking at complex numbers in polar form, so do powers. And so from this we get theorem 2.2, which says giving any complex number, then we have r comma theta to the n power is simply found by taking r to the nth power comma n theta. Okay, suppose that z is a complex number. Then the set OZ equaling z to the power n for all natural numbers n is called the orbit of z. So what we do is basically use our previous formula, the fact that in polar form r comma theta to the n equals r to the n theta, in order to compute the orbit of a complex number. Now once we actually repeat, then we can stop the orbit. So here I don't show the derivation, but surely you should look at it. Here of course r is 1 and theta is pi over 3. So our first z in polar form is 1 comma pi over 3. That would be z to the first power. Here for z squared, again, you simply take 1 squared, which is 1, and then you multiply 2 pi over 3 by 2. You continue that pattern, and then the last one you'll get is 1 comma 6 pi. Now that is z to the 1, 2, 3, 4, 5, 6 power. So the last thing you may question is, well, what about z to the 7th power? Well, z to the 7th power would be 1 comma 7 pi over 3. But of course 7 pi over 3 is simply pi over 3 plus 2 pi, and we know that pi over 3 plus 2 pi is equivalent to pi over 3. So the orbit is complete. Now not all orbits are finite. You can have an infinite orbit, but this is a case of a finite orbit. You can look in your textbook and see a case of an infinite orbit. Geometrically, if we were actually to graph this, what we would get is a regular hexagon. Last up, I just want to mention this, and that's roots of complex numbers. If n is a natural number, we know any solution x to the equation x to the n equals a is called the nth root of a. Well, if a is an nth power of x, then x is an nth root of a. We do want to note that x equals 0 is the only nth root of 0, since x to the n equals 0 for all x. Now we do have existence of nth roots when we're talking about non-zero real numbers. So x to the n equals a, where x is 0 number. On page 61 you'll see conditions for that. Also, you should compute all the fourth roots of the complex number a equals square root of 3 plus I. See example 2 on page 61 for guidance on that one. That will definitely be on your homework. Alright, that's a brief summary of section 2.2.2. Please let me know if you have any questions.